Have you ever wondered how Siri predicts your next words while typing? Or how Netflix recommends what to watch next? The magic behind this is a powerful neural network called Recurrent Neural Networks, or RNNs. In this video, we'll break down what RNNs are, how they work, their equations, and the challenges they face, like vanishing and exploding gradients. Let's get started. In a normal neural network, all inputs are treated as independent of each other. But in real life, data is often sequential, where the order matters. For example, in a sentence, the word "I love pizza" makes sense because the words are in the correct order. If you flip the order, "pizza love I" doesn't mean the same thing. This is where RNNs come in. RNNs have a hidden state or memory. They remember past information and use it to predict the next step. Think of it as reading a story. Every new word changes your understanding of the story based on what you've already read. RNNs can handle different types of sequences. One-to-many, like generating text from a single input. Many-to-one, for example, sentiment analysis, where a sentence is analyzed for emotion. Many-to-many, like translating a sentence from one language to another. Imagine you're reading a story. Each new word you read updates your understanding of the story. Similarly, an RNN works by passing information through a loop. Let's break it down step by step. It takes the current input, let's say a word or a data point, combines it with what it has learned so far from the previous inputs using something called the hidden state. Then, it makes a prediction based on both the current input and the hidden state. This looping mechanism helps RNNs maintain context, which is essential when working with sequential data. Now, here's the math behind it. Don't worry, it's simpler than it looks. At each step, the hidden state, denoted as h of t, is updated using this equation. Here's what this means. H of t minus 1, the hidden state from the previous step. X of t, the input at the current step. Weight matrices decide how much influence the previous state and current input have. And finally, the output, denoted as y of t, is calculated using another equation. This converts the result into probabilities to make predictions, like guessing the next word in a sentence. Let's break down how an RNN processes sequential data over time by unrolling it. At first glance, the RNN appears as a single unit with a looping arrow, representing its memory. However, this unit is repeated for each time step of the input. This is called unrolling the RNN. Imagine we're processing a sentence word by word. For every word, the RNN performs 3 tasks. 1. Take the current word as input. 2. Combine it with the knowledge stored in the hidden state from the previous step. 3. Produce a new hidden state that captures both the current and past information. This hidden state then flows forward to the next time step to process the next word, forming a chain of dependencies. At each time step, the RNN generates an output, yt, which depends on the hidden state at that step. For example, if we're predicting the next word in a sentence, each output is a guess based on the sequence of words so far. Now, from these outputs, we compute a loss at each time step. This loss represents the difference between the predicted output and the actual target. By summing up the losses from all individual time steps, we calculate the total loss, completing the forward pass. During training, this time-dependent loss structure means that we must consider how information flows through time. The network learns to optimize its parameters by minimizing this total loss, which ensures that it captures both short-term and long-term dependencies in the data. Training an RNN involves a method called backpropagation through time. Let's understand this step by step. At each time step, the network processes the input, updates the hidden state, and produces an output. A loss is calculated at each time step by comparing the predicted output to the actual target. These losses are summed to calculate the total loss. After the forward pass, the network computes gradients of the total loss with respect to its parameters. But here's the twist. Because the total loss depends on contributions from all time steps, the gradients must flow backward through time. The gradients are used to adjust the weights and biases of the network, step by step, to minimize the loss. Using techniques like gradient descent, the parameters are shifted in the opposite direction of the gradients to reduce the loss in future predictions. Training an RNN is computationally intensive because the gradients flow through the entire sequence. This means the network learns not just from the current input, but also from the temporal dependencies across the data. Despite their potential, RNNs face two major challenges during training: exploding gradients and vanishing gradients. Exploding gradients. When gradients grow too large as they flow backward through time, they can destabilize the network, making it difficult for the model to converge. One effective technique is gradient clipping. This involves setting a threshold value. If the gradients exceed this value, they are scaled down to remain within a stable range. Vanishing gradients. On the other hand, vanishing gradients occur when gradients become too small as they propagate backward. This is particularly problematic for long sequences where the network struggles to capture long-term dependencies. For example, if you're reading a story, the network might easily recall details from the last few sentences, but fail to connect information from the beginning of the story. Why does this happen? The gradient becomes smaller and smaller with each time step because of repeated multiplication by small values. This leads the parameters to focus on short-term dependencies and neglect the longer-term ones. Activation functions. Using functions like ReLU instead of tant can mitigate the issue by preserving stronger gradients. Weight initialization. Properly initializing weights can help maintain gradient stability. Network architectures. Advanced architectures like LSTMs and GRUs were specifically designed to handle the vanishing gradient problem by introducing mechanisms that allow them to retain long-term information more effectively. These challenges highlight why understanding gradient behavior is critical for training RNNs and why innovations like LSTMs have become so important for tasks involving long-term dependencies. RNNs are powerful, but as we discussed, they have limitations, especially when it comes to handling long-term dependencies. So, how do we overcome these challenges? That's where LSTMs, long short-term memory networks, come into play. In our next video, we'll dive into LSTMs, explore how they work, and learn why they're so effective at solving the issues faced by RNNs. Don't forget to like this video, subscribe to SmartSlides, and hit the notification bell so you won't miss the next episode in this series. See you in the next video.